I've got the lab set up and we're ready to go with the experiment on chromatography. I've got my 3 dyes, my red, yellow, and blue, and an unknown that Marianne put together. We'll find out what it is using this chromatography. I have chromatography paper here, and as I followed the instructions, I put in a line 1 centimeter from the bottom and then divided it into 4 little spots where I can put my red, yellow, blue, and my unknown. I worked ahead of time to make sure I got these toothpicks that are color coded, because otherwise I'm sure I'd mess things up. So I'm going to take the toothpick, which has been soaking in this red dye, and put as small of a dot as I can where the red is. I want a small dot so that it originates, rather than it being a big blob, into a very small line so I can see any separations. And I'll do the same with the yellow. One of the real strengths of chromatography is that you can have nano amounts and still be able to discern what these substances are. You don't have to have, milliliters. I should be a little bit more careful there. We'll see how that one spreads out, and I'll try and be even more careful with my unknown. I cut the tips of the toothpicks off a little bit so they soak up things a little bit better. There. I'm hoping that they dry out, but I really want enough so I can see, so I'm going to double these by putting another little dot and letting that evaporate over, making sure that it has a chance to dry out. And the same thing with the yellow and my blue. I love this color coding, as I know I messed these up. The food dye I just used a couple of drops of. If you were to try and weigh the amount of dye in these solutions, there isn't a balance in the world. Well, maybe there is, but there's none that I could afford that could weigh the actual mass amount of these dyes. They're visible because this is photons of light, and we're good at getting single photons. It's amazing that these dyes have such an intense color, and we'll deal more with color when we do a later experiment. There's my yellow, and here's my blue again, and I think 3 drops are going to be enough when this separates out. There. Nano amounts in terms of moles of each of the dyes that are used here. Now, we've used these standard food dyes that are the only ones that are available for food consumption, and I've got them on my chromatography paper. Now, rather than curling this up and taping it together, I've had difficulty with that. Very often the tape comes off. I'm going to try another technique where I take a petri dish and I'm just going to curl. I pre-curled this paper a bit, so it's got a little bit of curl to it, and here it is curled up and it's able to stand up on its own. Basically, you want to have the chromatography paper vertical so that the water that I'm going to use is going to use its capillary action to come up. There's ways of doing this horizontally too, but in this case, the vertical one's sort of a tradition, and I'm going to follow that tradition. And now I'm going to put in just the right amount of water so that the water comes to the bottom of the chromatography paper and gets a chance to gradually wick up, and we'll see the competition between the water molecules, solubility, and attraction to each one of these dyes and their components, and these dyes' attraction to the cellulose wood fibers in here. The water is going to wick up, and if the dye is really, really attracted to the water more than the paper, the cellulose, then it's going to travel with the water. But if it's more attracted to the cellulose, then it'll just stick there rather than move. So let me get that water, which I've got prepared here, some pure water, and I'll just put in enough to make sure that the water gets a chance to make contact with the paper, and I don't run dry within the time, but not so much so that it reaches up into the dyes and sloshes and dilutes the dyes. I think I've got it there. Looks good. I got maybe 1/4 to 1/2 centimeter of water in this Petri dish. Now, to help things along, I'm going to, or to make things work, I'm going to put this beaker around the beaker. Doesn't have contacts so that that paper isn't pressed against the beaker, but it's going to be there to prevent the water from evaporating from the chromatography paper. I don't want the chromatography paper have the water dry before it gets all the way to the top. So that's what we're going to see. And I think we've got all 3 of these dyes now there. We can see them nicely, and we're just going to be patient to see what happens. I'm going to start my timer. There we go. Timer starts, and we'll give this some time. If you want, you can go and do some calculus homework, or even play some chess, or maybe even do some chemistry homework if you like, because this is just a matter of being patient and waiting. I'll be here to make sure everything works out right, but Dave, you can go maybe even help make dinner. So let's just watch this stuff go. I'm going to fast forward. It's been about 1 hour and 16 minutes. As you saw, my chess clock had stopped partway through, and then I've reset it. 1 hour and 16 minutes, enough time to finish about 50 multiple choice questions on AP Chem exam, or maybe 2 or 3 AP Calc questions. But as you can see, the water has gone up and dragged some of these dyes with them. I'm going to take the beaker off right now and lift carefully the chromatography paper out of it. And I've noted where the lines have stopped. This is the limit right here. In fact, I'm going to draw that because I'll need to know the limit of the solvent, the water, where the water is gone, and we can see this separation. We're going to analyze that a bit later. I noticed that both the blue and the yellow traveled about the same length, and I need something to separate these two a little bit better than that. So what I've already done is I've put together another chromatography sheet, as you can see, with the same dyes, same type of paper, everything. And I'm going to do another chromatography experiment, except this time is, instead of using water as my eluent, as my solvent that's going to travel up my chromatography paper that I have here, what I'll use, as this is drying, I'm going to repeat the experiment, but I'm going to repeat it, let that dry to the side. I've lifted it up a bit so it can dry better. And I'm going to repeat it using a different solvent. And the solvent I'm going to use is propanol. Yes, here's my chromatography paper with its red, yellow, blue, and unknown. I have my water version drying right now, but I'm going to use a different solvent. It's referred to as 91% isopropyl alcohol, but actually the proper name for it is 2-propanol. It's an alcohol. It has hydrogen bonding, so it's going to wick up through this paper, but it also has a carbon chain, and this 3-carbon chain is going to have some London forces, so its intermolecular attractions are going to be different than that of water. And this will be nice because I'll have a different attractor for these dyes, and we'll see how they react to the propanol compared to the water, and of course to their stationary phase, which is the extreme hydrogen bonding that you've got in cellulose. So I'm going to take this and put it back in here so it's nice and curled. We've got a good view of, we've got a good view of the red, yellow, blue, and there's our unknown. Yeah, on the side, good. We can see all of them. And now I'm going to take the propanol and pour it into the bottom, the 2-propanol. There's a 1, which is a little bit oilier, but that's hard to get a hold of. This one I managed to get As you can see, it's a standard item in many pharmacies, and it's 91% and the rest is water. So I put that in there. Another common solvent is acetone, but you can't use that with this polystyrene sheet because polystyrene will dissolve in acetone. So I'm setting things up just as I did before. I'm going to set my timer. This time I made sure it's wound up so we can see what the actual time is using that timer. I've got it going, and we'll do some more calculus problems and see what happens and compare the water with pure hydrogen bonding to that of the 2-propanol, which has got some very nice London forces, and compare the two on the dyes. That'll tell us a lot about the dyes. Maybe we'll have a different type of separation than we have here. I'm going to just move a few things around, and I'm going to wash this out, because if these dyes dry in here, I'm never going to be able to clean out this reaction plate. So we'll see how long this takes and let the video do its thing. Here we are. I think we're at the end of the propanol experiment. I'm going to take the lid off, and we'll separate the chromatography paper. And boy, this is a pretty one. Look at that very, very straight line. I only have to put a pencil mark there to find out what it is. But it's also very strange about this purple here. I have to do a little bit of investigating on it. This is a very, very neat chromatograph. And let me let this stuff dry, and we'll come back to talk about it. Let's take a short look at the food dyes as we're going through the chromatography. I used the Mccormick food dyes. Mine isn't quite as old as this, but it's pretty old. We're dealing with red, a yellow, and a blue in these little dropper bottles. It's pretty classic. They still use them. Now, in the chromatography for the red, we found that there were 2 dyes that were present in the McCormick red. It was red dye 40, which absorbs in the green to cyan range, and red 3, which absorbs light in the green range. Of course, if it absorbs the light, that means other light comes through. And here you can see their structures. Typical for dyes, you've got alternating pi bonds everywhere. Here's a pi, not sp3, pi, sp3. And this sort of arrangement ends up creating a aura of electrons around these carbon chains that can absorb photons of visible light. The number that you have here will determine the wavelengths that are absorbed. Here's the red 40, and here's red 3. Red 3 is a bit different because it has a lot of iodines around it. Let's look at our chromatograph that we had with the propanol. And here it is. We've got our red dye 3 and red dye 40. Now notice in this reaction we had one substance that went with the propanol. Now I determined that that was red number 3, and the way I did that was that I knew that blue had red 40 and blue 1 in it. If that was on the label saying the blue was red 40 and blue 1. They sort of mixed two together to get their characteristic shade of blue. Since there was no red streak here, I had to presume that the red 40 didn't show up because it doesn't dissolve in the rubbing alcohol, the 2-propanol, very much. So this had to be the red 3, and the red 40 is stuck back here in the dot, just like it is here, mixed in with the blue. Oh, let's look at the water version of that red dye. Here's where I think that red 3 is, and here's where I think the red 40 is. But we'll get back to that later, because let's just look at red 3 for just a second. The common name for red 3 is erythrosine, and here it is with its iodines all around, and it's alternating double bonds which create that color. This isn't used very much. It's more of a pink. About the only place you'll find this nowadays, because it's been banned in a number of places, is in pistachio cells, certain cake decorating gels like the one I use, and very often in maraschino cherry, surprisingly not. Here's the color that they list for it. It's more of a pink
than a deep red. So there's the erythrosine, and here it is with maraschino cherries, and here it is with pistachios. And in our chromatograph, we've got it traveling along with the rubbing alcohol. In fact, the 2-propanol did the best job with red 3 in terms of having it attract to itself. These other dyes, the yellow 5, the red 40, and the blue 1, didn't travel very much compared to that. That's one of the things that we learned from this. Now, this red 40, when we did water with it, it traveled. It moved with the water. It had to be more attracted to the hydrogen bonding of the water, and it went with the water and didn't stick with the chromatograph here. The water traveled up here 6 centimeters, and this red 40 moved up 3.5. It had a retention factor of about a half. So it traveled with the water quite well. And here you can see, again, this confirms what I have here. The red 40 is present in the blue dye, and here it is at almost exactly the same ratio that we had here when it was all by itself. Now this red 40 absorbs at 504, and you can see it's got quite a different molecular structure than the red 3. In terms of use, it's used a lot more than the erythrosine. It's the most common red dye. It's considered to be relatively safer, and again, it's used basically the same thing. It's referred to as Allura red, and if you look at its color, it's got a much deeper red. So if you've got something with this really, really almost crimson color to it in terms of food, it's probably the Allura red. And in our chromatograph, we noticed that this was attracted to water much more than the red 3. So that's one of the things we can determine here. Here's the red 40 with 2-propanol, and here's the red 40 with water. Now the other substance we have here is this yellow 5, which didn't like the 2-propanol at all. I shouldn't have used like, but didn't have intermolecular attractions to the 2-propanol. That's our yellow 5. And as a food color, you can see its structure is very similar to the red, but it absorbs at 425. Its length of conjugated bonds is a little bit different than the red is. It absorbs basically violet light to give its own yellow coloration. It's called tartrazine, and nice, again, alternating double bonds, not quite as many as you've seen in the other substances. And here's its yellow, the FD&C yellow 5, very, very definite yellow color to it, as you can see here in solution, and it's water soluble. FD&C yellow number 5. So if you've got a drink with this yellowish color in it, or some combination of it, you know that this is going to be the tartrazine. And we found in our chromatograph that here's our tartrazine with no attractions whatsoever to the 2-propanol compared chromatography paper, which probably has a lot of hydrogen bonds. But here, when we use water, it traveled immensely. You can see 4.8 centimeters. It's even more attracted to water than our red 40. Now notice there's a little shade of pink here, so I bet there was a little bit of red 40 in with this yellow. I don't think I contaminated it, but I bet you that it was probably in that food coloring. So there's our tartrazine, and we would say generally this has strong attractions, hydrogen bonding most likely, to the water molecules and not so much to our fixed media, which is the paper. Now we can go to this. We've already talked about the red 40, which was here. And now we've got our blue 1, referred to as brilliant blue. Here it is. Absorbance is 628. It absorbs red light. So basically that red light that hits it is stuck there. And the reflected light coming out as a strong blue. And again, look at those number of conjugated bonds. And here's what we've got it on Wikipedia, our brilliant blue. In fact, look at that name. I mean, imagine trying to figure out the structure based on the name here, where we've got disodiums. It's a double sodium salt, which allows it to be soluble in water, just like all of our other dyes. There's sodium salts, so they dissolve in water. If you got rid of the sodium portion of it, you would end up having something that would be insoluble in water. And here's its amazing structure. So let's go now back to our chromatograph, and we can see the blue move beautifully here with the water. And here with the propanol, it hardly moved at all. 0.8, a little bit, certainly more than our yellow 5, enough so we could identify this blue and also identify it in our unknown. In fact, this would be a good way to identify our unknown because we see we've got this blue in it. And indeed, I checked at the very end. She said, yeah, put some brilliant blue in there. And this green here is the result of the yellow staying behind. The water chromatograph is interesting because the yellow moved up too, and so did the blue. And you can see them mixed here, making our beautiful little coloration, this green. That's the result of it. Now remember, the blue dye had a little bit of red 40 in it, which had a D of 3.5 or an F of about 50%. Here it is too. So this was the red 40 that was mixed in with the blue. It wasn't a separate blotch of red that was put in there. So we see its little faint level there. So we've done our chromatograph. If you do the ratios of the solvent divided by the dye distance, you can get the retention factor. And the closer that retention factor is to 1, the more that substance will move with your eluent, the solvent that you use. The less it moves, as in this case, we go back to our, here's our propanol, as in case of yellow, where we have a retention factor of 6 divided by 0.1 of almost nothing. Our R factor is close to 0. It means that the dye that you're using or the substance that you're using this chromatograph for is more attracted to the stationary phase, in this case the paper, than it is to the eluent. Now there's one interesting factor here that I'm going to check out later on. On the chromatography paper, I got the shadow of blue here at the top with the propanol, but not with the water. My guess is that this chromatography paper has some bluing in it. Sometimes they'll add a slight blue dye to paper and fabric, which is sort of yellowish to make it look whiter, and I bet that's what's here. I've ordered some of this stuff. It's referred to as bluing. In fact, it used to be used in laundries all the time to make dingy yellow fabrics and clothes look whiter by adding a little bit of blue to it. And I'm going to see how it reacts to propanol, the bluing agent that I'm going to buy. And you can still get it. It's sort of a classic substance. I've ordered some Mrs. Stewart's concentrated liquid bluing, and I'm going to take this bluing and put it on some filter paper, and I'll see if I run some 2-propanol through it, it soaks it out and creates that little ring that we saw before. So that's a future experiment that you can look forward to seeing.